Today we will be covering standard QPR1 for pre-calculus on completing the square. By me, Laekin Allen. The general goal of completing the square is to take any 2-degree equation, in our case with 2 variables, and convert it into this standard form. We'll see how this will be helpful to us later on, or you might already recognize this form and its benefits. So keeping this form in mind, let's think about factoring, specifically with perfect square trinomials, like this one. This is a perfect square trinomial because it can be factored out into a single quantity squared. So let's look at an example. This equation is not already in the standard form. To get it into the standard form, we want to look at the x components and y components separately. This way, we can complete the square for each individually. First, let's look at the x expression. We can see that our expression closely resembles x squared plus 6x plus 9, which is a perfect square trinomial, since it can be factored into the quantity x plus 3 squared. Now, how do we know that 3 was the number that went inside our quantity? There's a trick. The trick is to look at the coefficient of our x term, in this case 6. We take this coefficient, divide it by 2, and this is the number that goes inside our quantity. In this case, that number is 3. Now let's take a look at our y terms. So our expression was y squared plus 2y. So to make this a perfect square trinomial, what do we need to add and how will this factor out? So again, using our trick, let's look at the coefficient of our y term, in this case, 2. When we divide this by 2, we see that the number that will go inside our quantity is 1. Now, factoring this out, we can see what needs to be added to our original expression to make it a perfect square trinomial. By FOIL, we get first y squared, outside and inside 2 times 1y, and last 1 squared, which simplifies to y squared plus 2y plus 1. Now let's look back at our original equation before we completed the square. We can now insert our new x and y expressions where the old ones were. Since we added a total of 10 to the left side of the equation, we must also add 10 to the right-hand side to make this okay. Factoring our new expressions into their respective quantities squared, we can see this equation now takes the form of the standard equation that we introduced in the beginning. Let's take a look at a second example. Again, we're going to want to separate the x terms from the y terms. Using our trick, we take the coefficient of the x term, 10, and divide it by 2, giving us 5. Thinking how that will factor out, we will need to add 25 to our original expression. In the standard form, this is the quantity x plus 5 squared. For the y expression, we take the coefficient of the y term, -4, divide it by 2, giving us -2. When foiling this, we need to add 4 to our original expression. In the standard form, this is the quantity y minus 2 squared. Now we want to plug in our new expressions into the original problem, being sure to add the appropriate number to the right-hand side as well, in this case 29. When factored, we again have our equation in the standard form we desire. So why is this helpful? why do we benefit from equations in this form? Based on the recent graphs we've been studying, see if you can recall which types of graphs this equation generally represents. Circles. That's right. This equation generally graphs circles. So if we look at our two examples, after we had completed the square for each, we can compare these to the standard form of the equation. Each equation, we can see, has corresponding values for A, B, and R. Knowing that this equation represents a circle, we know that the coordinate AB gives us the circle's center, and R gives us the radius of that circle. So from this, what are the centers and radii of our two examples? For the first, since x plus 3 is the same as x minus negative 3, and y plus 1 is the same as y minus negative 1, we can see our center is at negative 3, negative 1. Also, since R is 5, the radius is 5. For the second, same thing. Since x plus 5 is the same as x minus negative 5, and we are given y minus 2, the center is at negative 5, 2. And again, since r equals 7, our radius is 7. So let's use this knowledge about circles to graph our first example. Using the standard form of the equation, we now know that the center of the circle is at negative 3, negative 1, and its radius is 5. So here is our center at negative 3, negative 1, and this is a point 5 units away. And using that, we can make a circle with radius 5. Here's a last example for you to try on your own. Pause the video and see if you can complete the square to work out the center and radius of this circle.